So we're here on number 9, and we're given, so the if is the given, and the then is the prove statement. Okay, so if you're ever faced with a problem with the if-then, if is the given, and the then is the prove statement. So we're going to start by writing our T-chart and writing statements and reasons. Our second step, right, first is write the T-chart, statements and reasons. Second is to number row 1 in both columns and write down given the given statements. So I'm going to go ahead and put 1. I'm going to write down the given statements is VZ, segment VC congruent to segment VY, and also WY, segment WY congruent to segment XZ, and then our reason here is given. Okay, great. So we have no more proof statements. So what do we do? Right? Well, we go ahead and follow this algorithm here. We're going to turn any congruency statements into equations using definition of congruent segments. So do we have any congruency statements? Yes, we do. We've got 2 of them. So I'm going to turn those into equations. VZ equal to VY, and also WY is equal to XZ, and it's going to be def of congruence. Okay, def of congruence lets us go from congruency statement to equation, equation to back to congruency statement. Okay, so what's my next step? Well, in my algorithm here, I have if midpoint is given, then I use definition of midpoint. Right? Is midpoint given? No, midpoint is not given. We're only given these 2 congruency statements. So we skip step 4. Step 5 is if we have 3 points on a line, we use seg-add-pos to create more equations. Right? Seg-add-pos lets us say first part of the segment plus second part of the segment equals the whole segment. So do we have 3 points on a line in this figure? Yes, we do. All right. Look, you might look at it and say, hey, it's a triangle. I don't know what's going on here. But we have 3 points on a line, namely those 3. Y, W, and V are all on a line. So we can apply seg-add-pos on those 3. What does seg-add-pos let us say? First part of the segment plus second part of the segment equals the whole segment. Namely, WY plus VW is equal to VY. Okay. Now, if you look at the bottom half of the figure, we have another 3 points on the line. Right? So we can apply seg-add-pos again and say Vx plus XZ is equal to VZ. Okay, let's do that. So number 3 is going to be, what's it? VW plus WY is equal to VY. And then our second equation is going to be Vx plus XZ is equal to VZ. And 3 is going to be seg-add-pos. Okay, so we have completed all of these steps. And lastly, we use substitution to get to the proof. So we're trying to prove Vy is equal to Vx. We're trying to get Vy is equal to Vx. All right, so that's going to be strange. How do we do that? Well, what I see, right off the bat, is Vy equals to that expression right here. That means anywhere I see Vy, I could put this expression. So do I see Vy in any other equation? Do I see Vy here? No. Do I see Vy here? No. Do I see Vy here? Yes, I do. So I'm going to take this expression. I'm going to put him in the place of that Vy right there. That is substitution. Now I'm looking at this expression over here. He's equal to Vz. What does that mean? That means anywhere I see Vz, I could put this expression. Do I see Vz here? No, I don't. Do I see Vz here? No, I don't. Do I see Vz here? Yes, I do. So I'm taking this expression, I'm putting him right there in the place of Vz, substitution. So that's step 4. Is going to be Vx plus Xz is equal to Vw plus Wy, and that's substitution. All right, so we're getting closer. All right. Now we need W equal Vx. We want these 2 to be equal to each other. We want these to go away. Right? We want these 2 numbers to go away. So they can go away if they're the same expression. Right? If we have xz and xz over here, we can make them go away by subtracting xz on both sides. So can I turn this wy into xz? Well, the only way to turn that wy into xz is substitution. And we need an equation that says wy equals xz. So I could substitute an xz right there in the place of this wy. Do I have that? Does this equation say that? No. Does this equation say that? No. Does this equation say that? No. Does this one say that? Yes, it does, dude. wy equals xz. So I could take this xz and I could put it right in there for wy. Okay? That's what I'm going to do. 5. Vx plus xz is equal to vw plus xz. Substitution. Now I want the xz's to go away. So how do I do that? Vx plus xz minus xz is equal to vw plus xz minus xz. 6 is subtraction. Subtracting the same number from both sides of the equal sign. Now, this guy I'm going to turn him to 0, and this guy I'm going to replace with 0. Right? These two expressions I'm going to replace with what they're equal to, 0. So 7 is going to be Vx is equal to Vw. And what is that? What's the reason? How can I take this and replace it with 0? How can I take this and replace it with 0? It's substitution. Lastly, I need a congruency statement. So I need to turn this equal sign into a congruency statement. So how do I do that? Well, first I guess I can flip it first, right? So 8 is, I need to flip it. So the VW needs to be on the left side. So VW is equal to Vx. And my 8, what lets me do that? Well, now I'm looking back at my proof sheet and which algebraic property here lets me do that. Well, a lot of you are going to say reflexive, but reflexive is same equals same. 5 equals 5, 7 equals 7, Vx equals Vx. Reflexive is useless until we get to proving triangles congruent. We're not going to need it. It's not reflexive. It is symmetric. Symmetric lets us flip the equation. Okay. So I come back over here and I flip the equation. That's symmetric. Last step, I need congruency statement. So I'm going to turn them back into congruency. And that is, of course, our trusty definition of congruence. Definition of congruence lets us go from congruency statement to equation. It also lets us go from equation back to congruency statement. And that's that problem there.